S parameters, scattering parameters, is the mathematical bridge that allows us to treat incredibly complex physical microwave components as simple, predictable black boxes. We first have to understand why we need them. At low frequencies, we characterize circuits using Z parameters, impedance, or Y parameters, admittance. To measure these, you have to apply perfect open circuits, I equals 0, or perfect short circuits, V equals 0, to the ports. At microwave frequencies, perfect open and short circuits are physically impossible. An open wire acts like a radiating antenna, and a short circuit has parasitic inductance. Furthermore, measuring absolute voltage and current at 30 gigahertz is a nightmare because the values change depending on exactly where you probe along the millimeter-length wave. Instead of voltage and current, microwave engineers measure traveling power waves. S parameters describe exactly how a network scatters these waves. The conceptual black box model. Imagine any microwave component, a filter, an amplifier, or just a piece of microstrip line. We place this inside a conceptual black box with two connections, called port 1, typically the input, and port 2, typically the output. Instead of V and I, we define our system using two types of waves: A waves, incident, waves traveling into the network from the outside world; B waves, reflected, transmitted, waves traveling out of the network. For a two-port network, we have four distinct waves: A1, power wave entering port 1, B1, power wave leaving port 1, A2, power wave entering port 2, B2, power wave leaving port 2. 2. The mathematics of power waves. To ground this in reality, the A and B waves are mathematically derived directly from the total voltage, Vn, and current, In, at a given port, normalized to the system's characteristic impedance, Z0, almost always 50 ohms. The equations for the incident and reflected waves at port N are shown here. These formulas are engineered brilliantly so that the square of the magnitude gives you the actual power, in watts, of that specific wave. Incident power and reflected power are shown here. 3. The S-parameter matrix. The S-parameters are simply the linear coefficients that link the incoming waves, A, to the outcoming waves, B. We assume the network is linear, meaning an output wave is just a combination of the input waves scaled by the network's properties. We can write this as a system of linear equations. B1 equals S11A1 plus S12A2. B2 equals S21A1 plus S22A2, or in elegant matrix notation, shown here. 4. Deriving the four parameters, the matched load trick. To solve for the four individual S parameters, we use a brilliant experimental trick. We cannot use perfect open or short circuits, but we can create a perfect matched load. If we connect a perfect 50 ohm resistor, a matched load, to a port, any wave that exits the black box and hits that resistor is completely absorbed as heat. Nothing reflects back. Step 1. Terminate port 2 in Z0. If we attach our source generator to port 1 and a perfect 50 ohm matched load to port 2, any wave leaving port 2, B2, is absorbed. Therefore, there is zero wave entering port 2 from the outside. This forces A2 equals 0. Now, look what happens to our linear equations when A2 equals 0. Deriving S11, input reflection coefficient, is shown here. Conceptually, S11 is the ratio of the wave reflecting out of port 1 compared to the wave we sent into port 1. If S11 equals 0, the port is perfectly matched, no reflection. In dB, this is your return loss. Deriving S21, forward transmission coefficient, is shown here. Conceptually, S21 is the ratio of the wave that makes it out of port 2 compared to the wave we shoved into port 1. If it's a filter, this is your insertion loss. If it's an amplifier, this is your gain. Step 2. Terminate port 1 in Z0. Now we flip the experiment. We connect the matched load to port 1, forcing A1 equals 0, and fire our microwave source into port 2. Deriving S22, output reflection coefficient, is shown here. Conceptually, this tells us how well matched the output port of our device is. Deriving S12, reverse transmission coefficient, is shown here. Conceptually, this tells us how much power leaks backward through the device. For a good amplifier, S12 should be incredibly close to 0. You don't want the output blasting energy back into the input.